All right, time for the last page, guys. Page 6. We're going to start by calculating the energy, wavelength, and frequency. Some of you are still having trouble figuring out these equations, but hopefully you'll have a little bit more understanding after this, okay? Please realize that these equations are actually going to be given to you. The DA reference chart actually gives you the equations, it gives you the constants, even though those weren't on your last one, okay? So those three equations, they look a little bit differently than we've seen them before, only because they're solved. Notice that this first one is solved for frequency, but it's originally the C equals lambda nu. Notice that frequency, instead of being represented with nu, is now represented with F. That makes more sense, right? Because we call it frequency. Anyway, frequency can also be equal to the energy equation, E equals h nu, or in this case, E equals hf. And then we have our third equation, E equals hc over lambda. Now, the speed of light, again, that's a constant that will be given to you. So that's 3 times 10 to the 8 meters per second. F is the frequency, L is lambda, which is what we call wavelength. And H is Planck's constant, and it has a value of 6.626 times 10 to the minus 34 joules times seconds. So when working with these types of problems, you need to follow the following steps. First, you want to identify which two variables are in the problem. Your only three options are going to be energy, wavelength, or frequency. So when you read the problem, circle those words. So in example 1, it says, what is the energy of a wave with a frequency of blah, blah, blah. It doesn't matter what the numbers are. Just circle the variables, okay? So now I know that I'm dealing with energy and frequency. Okay, now I go to the equations and find the one that has both energy and frequency in it. So the one that I see that has both energy and frequency is this one in the middle. So F equals E over H. From there, now we can go ahead and plug in the numbers and solve for the unknown. Okay, so then I'm sorry. You know what? Actually, let me back up a little bit. The way that this equation is given is not the most useful for our equations for this problem. We actually need the original version of that. So it's going to be E equals h nu. Because the question is asking for what is the energy, we want to have the variable of the unknown isolated on one side of the equation. Okay, from here, now we can plug in our numbers. Again, H has the value of 6.626 times 10 to the minus 34 joules times seconds. That value will be given to you, okay? You don't have to memorize it. And then for frequency, that number was given in the problem, 3.47 times 10 to the 15 hertz. Now, make a note to yourself. Hertz is 1 over seconds. So when I plug that into the equation, instead of putting hertz, put seconds, or I'm sorry, 1 over seconds. That allows us to see what units will be canceled. And then when I plug this into the calculator, remember that the times 10 is going to be, or leave that out, but instead use the second E button. So 6.626 second E negative 34 equals times 3.47 second E 15. Notice that each time I did not put times, I didn't put 10. The E takes the place of all that. Okay, so then now with your answer, obviously you're not going to write out all those numbers. You're going to stop with as many sig figs as is in your given. So since 3.47 is 3 sig figs, our answer should be rounded to have 3 sig figs. So the way we're going to round this is 2.30 times 10 to the negative 18. And the units that are left over after cancellation is joules. Oops. So 2.30 times 10 to the negative 18. Okay, for our next one, oops, I ran over the space there. Again, circle the variables that are in your problem. This one has to do with wavelength and frequency. So we know that the equation for wavelength and frequency is C equals lambda nu. Oops. Or in this case, because we're using F, C equals lambda F. Okay, so when I plug that in, or before I plug that in, I need to solve for the variable of the unknown. It says, what is the frequency? Okay, so since frequency is not by itself, I need to algebraically isolate the variable, okay? So to do that, I'm going to divide by wavelength, and that's going to give me the equation F equals C over lambda, okay? From there, now I can plug in my numbers. Again, C is the speed of light constant, 3 times 10 to the 8 meters per second, divided by the wavelength. Now, something to take note of is that this is already in meters, which is a good thing because it has to be in meters. Remember that if this was in nanometers, you would use the conversion of, for example, if I had 411 nanometers, then the quick and easy way of converting that to meters is 4.11 times 10 to the minus 7 meters. Please remember that. I don't know how it's going to show up on the test, okay? Anyway, take the 4.34 times 10 to the negative 7 meters. Okay, cancellation. I see that meters repeats in the problem, so it's going to cancel. And now to calculate. Okay, so we're going to say 3 second E8, enter, divide by 4.34 second E negative 7, enter. And then I end up with 6.91, blah, 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 blah. Again, don't write all those numbers. That's crazy at this point in the year. You need to know better than that, okay? So 6.91 times 10 to the 14. Okay, so units that are left over is this second, but notice that it's on a denominator. So it's actually 1 over second. And like we said, 1 over seconds is hertz. Okay, all right, now on to the multiple choice questions. And again, this is just a review of everything we've talked about. Electrons in an atom's outermost shell is called valence electron. Electron dot structure. I don't know if we actually mentioned this in class, but the element symbol in electron dot structure, like for example, let's say carbon with 4 electrons because it's in group 14. That C that we write in the middle, that represents all of the atom except for its valence electron. So the correct answer on this one is letter B. The symbol represents the nucleus and the inner level electrons. Number 3, how many valence electrons? And again, this is using the electron configuration in order to determine how many electrons it has. Okay, so notice that both of these are the third energy level, right? 3s and 3p. That gives us a total of 7 electrons for the valence shell. Boron's electron configuration, which of the following represents its dot structure? Again, you already know the cheat on that, right? That's that chart that we drew out where you take the last digit of the group number. That'll tell you how many electrons, but also the electron configuration does. So letter B on that one is the correct answer. Okay, beryllium, which is the following is its dot structure. That's the one with 2, right? It has the second energy level with 2 electrons. Which electrons represented by the dots in the dot structure that are represented in the dot structure? These are valence electrons. Okay, last part, we're almost there. Isotopes. You just need to memorize this. This is a definition, okay? You have to know it. An isotope is an atom of the same element that has a different mass number. Okay, that different mass number results from different number of neutrons. Because isotopes are the same atom, they should have the same amount of protons. So for an example, there are 3 isotopes of hydrogen. There's protium, deuterium, and tritium. They're all hydrogen because they all have the same atomic number, meaning they all have 1 proton. But the mass number is changing, and that's because they have different number of neutrons. This is a big important one. The most abundant isotope is the one whose mass most closely represents the average atomic mass. So an example of that would be like for carbon. Carbon has 3 isotopes also. Carbon 14-6, carbon 13-6, and carbon 12-6. Now, when I look on the periodic table, I'm going to see that carbon has an average atomic mass of 12.011. Since 12.011 is closest to 12, I can say that carbon 12 is the most abundant of the isotopes, okay? All right, so to calculate average atomic mass, you're going to use the equation EM, which stands for exact mass, times the fractional abundance, which comes from the percentage, but remember we have to move the decimal place twice over. Okay, so all we're going to do is move that decimal 1, 2, and I get 23.985 times 0.788. I'm also going to do the same for the next one, 1, 2. So 24.985 times 0.1015. And since I have 3 isotopes, I do this 3 times. 25.982 times 0.1105. Okay, with all that being said and done, I'm going to get those 3 answers, add, and then that is my final answer. Okay, so let's go ahead and do that. 23.985 times 0.788. That's going to give me 18.9. Do the same thing for the next. 24.985 times 0.1015 equals 2.536, and 25.982 times 0.1105. Okay, and that's 2.871. Okay, now I take those 3 numbers and add them up. 18.9 plus 2.536 plus 2.871. Boom, there's your answer, okay? 24.307. That's it. Good luck. Go back and study. I know it's a good lengthy packet, but I know you guys can do well. So study as much as possible and let's kill this DA. You guys have a good time.